Yeah, I'm Sunanda Iyengar, and I'll be talking about fire prediction using IoT data on AWS. So I was saying about AWS, about its computational abilities. It's because it's not only very high, it's stretchable. You can add more on-demand instances and stuff like that as you require, and you can remove them dynamically. So it's really good in that respect. And also it has almost infinite storage capabilities. I mean, they claim, I don't know, because I have not tested that. So so it's only logical that everybody who needs certain type of ML work progress towards AWS eventually. And they're doing everything to educate developers and all the tech people to know about AWS so that they can migrate, the corporations can migrate to AWS because this is a very nice enterprise solution platform. The ecosystem is very vast. It has huge number of components. So I'm sorry, sometimes I think I'm in and out of the mic. So I would like to tell a few things about AWS before I move on to the IoT data and also the ML algorithm, which is actually required to do the prediction. The two things are a little bit murky for me is the IoT data, because I have not used the data. I'm only presenting the architecture here. And I'm very curious to see if the participants have ideas about either the IoT data or they can have any information, because a lot of you are ML experts. So I'm pretty sure you can come up with some model, some suggestion about it. I do have one Kaggle model. Somebody, it's not working, but at least they have done some work on that. So in the event of implementation, they can, there's something, there's something to use. So having said that, let me go to the architecture diagram. And let me start from the extreme left. That's where our data is. That's where our IoT, it sits on the edge. It's not within the cloud. It's the IoT setup is sitting on the edge, and I apologize for the missing letters in the extreme left. It's what we collect is wind, atmospheric temperature, other things, humidity, if there is any rainfall, any other things that can pertain to our fire prediction. A large number of things are there available, what are called things in the IoT. So we can collect them, and I'm not very particular about what's the type of data, but this is the data that we need, and I don't have a working model, so that's why I'm saying this is first. Let's start with the architecture. Eventually, when I get to implementation, I'll come and talk about the implementation. So we have it's outside the cloud. We have what is called AWS Greengrass. This is the one that picks up the data from all the sensors, IoT sensors. It picks up the data and it does some processing, and then it sends it to the cloud. The first component in the cloud, the AWS that picks this up is Kinesis. It sends it through a protocol MQTT. This is a lightweight protocol, message queue telemetry transport. The telemetry is the keyword here, and then MQTT. I mean, of course, this is because we take the IoT data and we do all this processing there. So, and this is a fine protocol exclusively. I mean, I don't know where else, but for sure, this type of activities, we really like this because it's very fast. And therefore, we really need real-time processing. When you do this, we need to pick up the data, and then we need to give it to the ML model almost instantaneously. And that can happen with, I'm pretty sure it can happen with our AWS environment. So having said that, the data comes to what is called kinesis. If you're more comfortable with Apache Kafka, it takes and puts the data into what are called topics. That's the Kafka. So it picks up the data and puts it in Kinesis, which is equivalent to Kafka. But I'm not sure how close they are, but for sure they are equivalent. And from Kinesis, it just sits there. Kinesis doesn't do much. It just puts it in topics, and right away it needs to be picked up by somebody else, and that is Firehose. This Firehose is self-managed, very powerful tool that it can, along with another a tool called Glue, AWS Glue, they both together do what is called ETL, extract load, transform load. So when they do the transform, and what they do is they create schema for the data if you already don't have, and they add the data to S3, the S3 bucket. S3 is simple storage structure, AWS S3, and that's one of those things that is so big in terms of storage capabilities. And it takes any data form, as far as I understand, it takes almost various different types of RDBMS data, I don't know, vector data, anything, binary data, protobuf. So various different types of data. So it takes that, but we are more interested in tabular form, because we are able to do that through Firehose, although our input data just is picked up from the sensors. And here now in S3 bucket, it will be in tabular form. And then right away, it has to go somewhere else. We have to reach our final destination is our model. So in between, if you see the Flask-like structure, this is what is known as the step function. The AWS step function should not be mistaken for our step activation function. It's got nothing to do with that, ML models step activation. But step function, it's a very elegant tool. It has its origins in finite state model of theoretical computer science. This is a workflow model, and it has it comes across to users as if you create the workflow, it has a start node and an end node, and in between links, and you can put tasks, and these tasks you can sit on the links in sequential manner, one after other, between start and end. Several tasks and sit on one link, or you can put them in parallel, several links in parallel, or they can circular loops and all that stuff. From beginning to end, it can do a lot of things. And we are interested in a few tasks, not just one single task. I'll tell you, the most important task is, of course, to move it to the ML model. But the two other tasks I would like to just touch upon is it's coming down. So the pipe. So the workflow model is step function. One of the tasks would be the Lambda. It sends it to the Lambda. The tasks are actually Lambda, AWS Lambda functions. This you can somewhat draw a parallel to our anonymous inline Lambda function in Python. So you can draw a parallel. It's not anonymous, but it is serverless. So the Lambda function, it operates in serverless environment, and so it's a microservice. So very small piece of code for each function. So so you can have many microservices like this, which is popular now compared to the monolithic structures we used to have. We still have. So the serverless Lambda function, okay, it picks up the data, and it is trigger activated. So the Lambda function is not. It has to be activated through the step function, and it picks up the data and sends it to the SageMaker. AWS SageMaker is our ML. You can deploy our ML models on that, and it will do the prediction. that's where it ends. So the SageMaker is a very cool tool. It has if I'm not wrong, it has a Jupyter lab, I believe, and you can actually train. You can train ML models on it, and then you can deploy the model right there. And it actually takes the model. There is a what is called the Bedrock. AWS Bedrock actually hosts a whole bunch of models, Anthropic model, Hugging Face, even Metalama. All these models are there on Bedrock, and you can choose your model. And in fact, there is a Amazon homegrown model series called Nova. So there are a lot of things. Probably you can bring your own model as well. And Bedrock is a API. You can use that to connect to SageMaker, and that will predict. It will the model sitting on SageMaker will now use your data, and it will predict the fire outbreak. So that's the thing. But my faith in this increased the moment I did this simple structure architecture. I saw that there within a few short hours something surfaced and it had a slightly elaborate, a lot more sophisticated architecture, which used all these components and plus more for more other things. So this works. It's not a novel idea or anything. The moment Greengrass came out, the whole thing might have come out. But having said that, I do not know if CalFire is using it. Who is using it? I don't know why we have so much trouble. And in fact, I'm a lot more interested in also seeing if we can have a model that can, it's a side issue. I'm not, this is my main issue is IoT for wind and atmospheric things. But we have a lot of problem fires in California due to arson. And I think the FBI should find somebody to do these models for arson also, arson prediction. I don't know how they can do it, but it has to, but by various types of data collection about people, they can do that. I don't know if it will infringe on the privacy. I don't know. I really don't know. So I'll leave it at that. No, but anyway, this fire outbreak prediction, this can actually go to, again, controlled by the tasks on step function. It can go to what is called, get the name of that, the CloudWatch. The CloudWatch can provide alerts if there is a serious issue with that. The CloudWatch will provide alerts to us. Also, there is what is called another CloudTrail. It will display the logs continuously. You can put logs from various different parts from the ecosystem. You can put it in CloudTrail, and you can monitor the logs. Those things are there available for us to take advantage of. So CloudWatch, yeah, and that will display the alert. And pretty much, I think I've covered the most important parts. So yeah, and this is about AWS. If anybody is interested to talk more, I can ask a question. I can tell. So I just have the components listed here. The MQTT protocol is the most simplest of the things to rapidly collect data, and all these other things. Other components can do rapid movement of the data, and we can get a prediction, and from there, and the data in some manner is available. California weather and fire prediction data set, and then forest fire data set on Kaggle, and then there is a small model. I tried to run it; it failed. If anybody is interested, they can go see if they can fix that. There's some small bug. They can fix the bug and see if they can get the prediction. I didn't do much research on these things, but I just wanted to tell folks that it is available. They can do it. I'm not very interested in implementing this architecture because I'm pretty sure somebody else would have done that. This is the beginning of various different architectures that one has to learn the components of AWS. There's no escape from that. Very complicated. It's a huge ecosystem. If you really want to do a good job of architecting enterprise level solutions, take it from me. very difficult. You have to spend 3 months dedicatedly to know all these things. What is the AWS offering? And it's important also to know these things. Reason being, sitting at home and deploying on some free websites for low traffic is a different story. If you have a powerful ML model, you want to take advantage of their computational abilities, and particularly corporations, and they have all these aging people, techies. They can all train themselves. They know so well. They've done web technologies, REST protocol and stuff like that. If you know REST protocol, you know all other things. So I'm just making a joke. So, but anyway, so that's about the data. Next part is questions. I don't know if I took too much time. So if there is time for questions, I'll take them.
Was this set up as a public competition on Kaggle, or is
the architecture was not?
Okay.
The model, I stumbled at it yesterday because honestly, Ted suggested what is the status and things like that. It is just architecture. So I want to get a feedback. So I'm going to say, on Kaggle, there is a model that will predict fire. I don't know what data it will take and stuff like that. And the other data is coming from Cal Fire. The two things I showed. One is the data, and the second is Cal. So the model is with Kaggle.
Okay.
I can share the link.
Thank you for presentation. Could you please move on to the diagram?
Yeah.
I think it's SO3, it's a step function, right?
Yes, yes.
And could you please collaborate more about what functionality it's like involved? Because in my understanding, it could potentially orchestrate sequential execution of Lambda functions, right?
No, Lambda function is different. Step function is different. The step function is it's workflow. If you are familiar with N8N or the website, I space out on that. But if you know N8N, it has this huge workflow. People, they don't see this because it costs money to do these things on AWS. But N8N, the workflow architecture is there. So other one is make.com. So they have workflows too, if you see them. But they are a little different. That's workflow automation, make.com. So the step function is also for workflow management.
Okay, so like technically you're calling just one Lambda function from your step function.
Yeah, it operates on the principle of state transition. If you have had some class in theoretical computer science, and it's not mandatory or anything. It's a very simple thing. On AWS, the step function is you have a start node and an end node. I should have put a picture, but I got it very end. So the start node, you put it circular manner, and then you connect the links from start to end. And on the links are your tasks. The tasks, once the task is accomplished, it's called a state transition has occurred. The jargon is borrowed from a finite state model, finite state machine. And if you just Google that, you will know what the finite state machines are. So, and
thank you. I think I got the answer, yeah.
All right, thanks.
No, I just wanted to answer his question about, the step function and the Lambda. Step function is just like to connect different AWS services. You will need something in between, and that's what she was telling, that there would be some nodes that would be connecting just to connect different services. And when you go to Lambda, you would want to write some function without worrying about, which server am I hosting? I need a base server. So the AWS just created different services. One is Lambda and second. Just a slight difference. Can you connect PyHeroes directly without? You can, I believe, right? It is, while in production, you would need to have such a kind of a pipeline. But if you're creating a small project of yourself, you can directly connect S3 sitting in SageMaker. Am I right?
Absolutely.
Yeah.
I put step function with an exclusive intention of actually saying that it goes to the CloudWatch for for alerts, and it
For
also
the
goes to
loggings and all of
logging.
that. Yeah.
All these things, they are different Lambda functions. I am not sure if they can be in series. They shouldn't be. That they will just be showstoppers sometimes. So you put separate links in parallel, and of course you can put some kind of caveat. Okay, you don't start till the prediction is over and things like that. That probably can be
Yeah,
done.
sure.
Other than that, you can step function is still a good one to be there because it is trigger activated. So when some other thing is ready, data is ready, okay, you can start your work for prediction. So that the SO3 is like a custom label. It's nothing to do with AWS. Uh, the software gave me that and I used it. SO3 I can call it Sunanda. It doesn't have to be SO3.
Another cool thing that you can actually do with a step function is you can actually have it like if you have an S3 bucket, you you can have a Lambda function iterate in batches over all of the contents of that S3 bucket, which is something that I've had to use before, and you can actually do that in parallel with multiple Lambda functions as opposed to just having one Lambda function run. It's super useful.
Yeah.
I guess my question is, did you implement like CloudFormation or Terraform, or have you considered
Yeah.
implementing those?
Yeah, very nice question. Thank you. Yeah, CloudFormation, some other application. We were doing something and policy.json had to be on the CloudFormation, and let me share that if you are interested. It's a SAM CLI workshop. Okay, SAM CLI workshop where your SAM is sitting on your local machine, and then the server is sitting on AWS, so the communication takes place back and forth. For that, I had to put the policy.json on CloudFormation, and these things have to happen. So some kind of bare minimal experience I have through working through these workshops and stuff like that.
If I can make if I can make a suggestion to now, this is just my opinion,
Absolutely, yeah.
if anyone is thinking about like whether to use CloudFormation or Terraform, I would heartily recommend Terraform because CloudFormation has this thing that it'll sometimes just lock up and stop its update. So in production, that's not like it'll stop for like an hour and your app will just be down for like an hour.
Very good suggestion, yeah.
Yeah. So I don't know. That's just my opinion.
Yeah, that's cool, yeah.
Terraform is
I mean, they should just make it YAML. Just kidding. I don't know. I didn't need Terraform for the SAM CLI workshop. I had to correct the policy.json and JSON, and the IAM will pick it up. Your IAM is very strict in terms of security. You have to have permission for everything. Bedrock, you have to have permission for SageMaker. Everything is coded in your policy files, and it's easy. Once you figure it out, it becomes easy. Yeah, thank you both.
All right.
I really appreciate you.
I think we're gonna move on.
Yes.
So thank you, Sananda. And if you go ahead and with this project and you build this, I'd love to know what sort of accuracy you get with your fire prediction.
Yeah, thanks. Yeah, I will do that. See if I can do some implementation if I have correct data.
All right. Thanks, Sananda. All right, we're gonna move on to our next talk. And Ryan, you're gonna talk about HRM and TRM. Yep. All right, and then we'll do monthly news after that.
Okay, cool. I have two different things. So we'll start with the TRM and then I'll talk about just the general monthly news after. Good to go? Still recording? Okay, perfect. So this super popular paper only a few weeks ago, TRM is what people have been calling it, but it is a follow-up to HRM, which is a even a little bit older paper, just like a month or two. So I'll just tell you a little bit why this paper is interesting first, and then I'll talk a little bit more about the details. So the general trend has been bigger models, and then also scaling up in terms of reasoning tokens. So we've got these models that they can like internally just think a whole bunch, and then they start outputting their answer. And so people have done a bunch of research on this, and they've figured out, okay, if we do this, we get a little bit better reasoning performance, but the slope of it is not very strong. And so people have been kind of poking at a bunch of different directions and saying, okay, we can't scale to 10 trillion, 100 trillion parameters, and then it only makes us 5% better. We need to find some different axes in order to get better than that. So this HRM and TRM papers are both pushing in that direction, saying like, well, there's this other scaling direction we can do where we basically say, let's loop our model and then teach it to get even better reasoning performance. And so the whole idea of HRM, it was largely inspired by the brain, and they said there's this hierarchical higher level and lower level loop, and then TRM came in and kind of simplified things and said that's not really the right way of looking at it, and so I'll talk about that a little bit. So for these papers, they were focused on a few different tasks. So maze, Sudoku, ArcAGI, and these aren't what you would think of in terms of like general reasoning. It's like, can they solve a puzzle? But people use this as a proxy for like how good are they at reasoning and problem solving. And so there's been this growing trend of people want a cognitive core, is what Andre Carpathy was calling it. It's basically this idea of like, we want a small model that's really good at thinking, but it doesn't necessarily have all of the storage. Like our big models right now have 1 trillion parameters and they've memorized every single fact, but you want them to be small and be able to just think like we do and be able to like ponder a problem for a little bit and then come to a solution rather than just memorizing the entire internet and like have it be able to map to its memory. So like I said, this came from this HRM paper, and they had all of this stuff in there about like it's inspired by the brain, and they said we have 2 levels of recursion. We have higher level and we have lower level. So we have these different frequencies. So the lower level is looping a whole bunch, and then it returns something to the high level, and the high level does a step. And so they showed basically, okay, it's converging over time on the low level, and then it's converging over time on the high level. And this is similar to how like we've scanned mice brains, and we've seen that it does this same process. And so they said, okay, we figured this out. This is how we get reasoning. We do this hierarchical setup. So they measured a whole bunch of things. So this is the graph I was talking about. So they're saying basically, look, our low level, it's doing a whole bunch of loops, and then it slowly kind of converges to some point, and the high level is going beyond that and saying, okay, the high level is converging to a point too. And so they were also measuring various different things in terms of how does our performance improve as we increase width? How does performance improve as we increase depth? And so the idea is you increase depth and it can do kind of more steps of reasoning, but the problem is you're also adding more capacity for memorization and other things of the model. And so they figured out they can do this HRM setup, and that gets significantly better performance per depth by having less actual layers. And I'll talk more about the details of that. So that's all I'll cover on HRM. I'll talk about TRM more because it's kind of just a simplification of HRM. They basically studied it and they said, these are the parts that actually matter. So we'll focus on that a little bit more. So the core idea behind TRM is basically just scale up looping instead of scaling up parameters. So the idea here is, I talked about, we have these models that are 1 trillion parameters, or people have done like, let's make it think for 1,000 tokens before it starts spitting out its answer. This is basically saying, let's take a 2-layer block and just pass its output back to itself. So the idea here is that it has very few parameters, so it can't like memorize the problem. It has to kind of generalize to whatever the reasoning is. So if you're doing a maze, for example, it needs to kind of traverse the maze and try options and then backtrack and stuff like that. Whereas if you have enough capacity, your model just looks at it and just memorizes the puzzle and says, okay, this is the path every single time. So if you limit it to only 2 layers, it can't do that total depth. So it needs to learn the like actual rule or transformation that's happening in order to get there. So the idea with TRM was you're doing this looping, but you're doing it at multiple different levels. So there's this outer loop that it's doing potentially 16 times. And then the inside of that is a high level loop and a low level loop. And this low level loop is happening many times. And essentially the idea that it's trying to get at is like figure out the reasoning for the next step. And then the high level is saying, okay, take the next step now. So we have multiple different variables that are being stored here, and I'll talk about those later on the next slide. But just understand there's like 3 levels of looping going on here. There's low level, and then that builds into the higher level, and then there's another outer loop beyond that. And so we can take our little, actually just 2 layers of transformer, and we're just saying loop it this way, loop it that way, and then loop it an additional time on top of that. And they built it to the point where it's technically 84 depth, but it's only still 2 layers. So here's the code. This is the entire algorithm basically. And so I'll move this out of the way so I can read hopefully. So I'll talk a little bit about this latent recursion process. So we're using this same network at every different level of this hierarchy. So you imagine you just have 2 layers. This is just being reapplied all these different ways. And so you're giving the model X, which is our input board. So imagine this is like your Sudoku that's not filled in yet. And then Y is the current answer. That's like what the model thinks like our prediction should be. And then Z is its reasoning. That's some embedding that's saying like, oh, I think we need to go this direction, and then that basically. So this latent recursion is saying do this many else steps, so the lower level, and then this final bit is doing the higher level. So the lower level is iterating on the Z, that's the reasoning part. The higher level is iterating on the Y, that's the actual prediction. So it's doing multiple loops saying, think about this a little bit more, and then it's doing that outer loop saying, okay, now update your prediction. And so it can do that process of like, think about this a little bit, figure out what the next step is, and then try to update that next prediction. So that's the first 2 inner layers of the loop. And then the outer layer on top of that, what they're calling deep recursion, is basically saying we can repeat this up to 16 times. So it thinks about its reasoning, it makes a step, thinks about its reasoning, takes a step, and then it does that a bunch of times. And then you can wrap that in another outer loop. And in that way, it's can take many, many steps. And one of the key points that they figured out is they can actually apply this latent recursion multiple times without any gradient. So not actually training on that portion. So imagine you pass it through the model through this latent recursion process 15 times, and then you only train on the last latent recursion. So it's kind of crazy that this works because it's going through so many steps of this model with no training signal at all, and it's just the last step. And what we're really trying to pull out is we want a model that is able to take these steps towards the solution and then just loop back into itself. So it can just keep trying harder and harder and harder. And I'll show a tweet later. People have figured out that it's actually trained for up to 16 steps, but people have extended it all the way to 400 something, and it's still getting better performance, even though it was only trained for 16. So if you understand this, like 24 lines of code, that's the whole algorithm, basically. So yeah, go for it.
Just a little bit of color. So this is not the first paper that has talked about recursive architectures. And so if you imagine like a common model that you have out there maybe has 48 layers, okay? Lots of people have shown that what you could do is you could have a 2-layer model and just repeat it, what did I say, 24 times, and it'll have the number of parameters in terms of how much GPU memory and everything you need will be very, very small because it only has 2 layers. But when you run it, it takes just as long to run as the 48-layer model because you have to repeat each of those 2 layers 24 times, okay? So it's not completely intuitive to me that repeating 2 layers over and over again 24 times can get you within 5-10%, whatever, of the performance of having 48 unique different, valued layers. But that's sort of a known thing here, okay? So I just wanted to kind of have that background. So when you see Ryan talking about like, hey, we're going to repeat this layer, 6 times, or we're going to repeat this 3 times, whatever, that's not the novel part here. People have already sort of done that. But this idea of sort of having these 2 separate thoughts, that that now is something that's very different here. Okay, but one of my, I don't know, personal rants is people talk about how tiny the model is, and that's true in terms of memory, but it's not true in terms of compute. And so if you have this thing and it loops 200 times, it's actually doing as much compute as, say, like a 3 billion parameter llama model. And so it's not really that tiny in the compute sense. And so it may be hugely beneficial in the long run because you can run it on devices that don't have a lot of memory or whatever. But just not to be mistaken when people say tiny. It's not tiny in every respect.
Yeah, it's small in memory, but if you look at the actual compute, then it's difficult. Yeah.
I'm trying to understand again what you're trying to say and what Ted was saying. It's little hard, little less intuitive to me. You're saying that there are 2 layers, and when we loop more times, it will learn better. But example, it's just 2 layers, less parameters. Won't it be difficult to generalize? It's just learning the same data and not generalizing it enough. So maybe in the new data, it will know that only the maze goes like this, and I just know this part. It will not have enough brain to, okay, we can find the other part. I mean, it's little difficult for me to understand. Can you maybe with some diagram help me understand better?
Yeah. So I have a diagram view if that's useful for you, but it's the same thing as the code, just with some color to it. But the idea is basically if you only have 2 layers, you can't memorize the puzzle. It just doesn't have enough parameters. It's very difficult for it to do that. So it needs to learn the rule instead of the actual memorization of the puzzle. So that's the theory behind it. I'll show there's a tweet where someone actually showed like all of the steps of the model trying to solve through all of the different steps. So it goes through 16 steps and is trying to iterate on the puzzle 1 step at a time. But that's the general premise is you don't have very many parameters, so it has to learn just the core principles rather than memorize the actual puzzle. That's the idea roughly.
Yeah, and also the examples that we're seeing, it's like solve a maze, solve Sudoku. It's nowhere near like able to chat with you like even GPT-2, let alone like GPT-5. So this is not yet a general purpose model, but it's an interesting new direction, and it's like an early proof of concept kind of a thing, I would call it maybe.
Yeah, I think the big thing is everyone's looking for the different scaling angle. Like right now, everyone's saying, okay, more compute, more parameters, everything. But it's interesting to say like what do we do for just like more effort? And so people are figuring out different angles for that. And so the interesting thing with this is they actually did various studies and they said, okay, we are using a certain amount of depth. What if we do 4 layers or more, or some other choice of parameters? And they found that like if we make this a 4-layer block, it gets worse performance than 2 layers. So in some way, that like 2-layer limit is your regularization, saying you can only learn simple patterns. So you have to learn the simplest pattern and then apply it multiple times. So that's very, very new research. So people are still figuring out like exactly how does this work, which parts are the like true signal and what's just kind of like extra garbage we mixed in. Yeah.
So I'm wondering, just intuitively, is it like trying to find it's like, say you're trying to like construct a wall, for instance. It's trying to find a brick that is able to be repeated, the same shape brick that's able to be repeated 16 times to produce a wall that's able to stand, basically.
Yeah, I think that's a good way to think of it. So one of the difficulties is getting stability in all of those loops. So if it has to loop through itself 16 times, it needs to be consistent in whatever it's doing. So that's one of the big struggles, is like whatever it's learning needs to be able to be passed back into it. It can't just be like print out the whole wall in one step.
Okay.
So here's the diagram that goes along with the code. So the way that this is constructed, you have the input X, which is like your starting board. You have your prediction Y, which is the current answer. You have the latent reasoning. And the way that these are merged was something that I was messing with a bunch recently, is they just add them together, which seemed a little bit strange to me because you're blurring together your input question, your prediction Y, and your latency. And so it kind of seems strange that at every loop, it's just adding these all together and just blurring them. And then you have you can do a transformer encoder block or different things here. They tried an MLP for one of the problems, but just imagine this is your input, your current prediction Y, your latency, and those are all getting merged together before it goes back through that repeated block many times. So this is talking about the different levels of recursion. So you have the low level that's happening maybe 6 times. You have the higher level that's maybe happening 3 times. That's what they found to be about the best they could do. And then you have the even outer layer on top of that can happen up to 16 times. And so one of the interesting things that they did, they were trying to do adaptive compute. So they said up to 16 times. So the model at every step of this outer loop is saying, am I already completed? If I'm completed, I don't need to do more steps. So in reality, it can do up to 16, but very often it was just doing 4. So it did 4 of these loops, and then it said, okay, I've got the solution, just exit. And so that's one of the interesting optimizations they could do, because if they had to do 16x of the H and the L cycle, and then through that whole training process, that's very, very expensive. And so if they can shortcut that down to 4, that makes it 4x faster to train potentially. So I haven't talked too much about the problems yet, but they worked mostly on these 3 problems. So ArcAGI is, we had a presentation on this a couple months ago. Sudoku hard. So these aren't your like run-of-the-mill Sudoku puzzles. These are very difficult, that like you need to know the algorithm and the different ways that you can solve very well. It's not simple problems. And then they also have maze extreme. So this is a 30 by 30 grid, and they basically say, here's your green starting point, here's your red ending point, figure out the path to connect these 2. And so you can see this is a pretty big maze that it needs to go find the path all the way through to the end point. So these are your 3 different problems. And so they train the model separately for all of these different tasks. So they have one model that's for ArcAGI, they have one model for Sudoku, one model for maze. So it's not a general purpose, like all combined thing. So that's one of the things where this differs. People were looking at this and they were saying, okay, GPT-5 and Grok and whatever, they're just very general purpose. You pass anything to them and then they can probably do a semi-respectable job at them. And this is like very narrow. So some people were pumping up this result and saying, oh, it's the best thing. And now just do that, but GPT-5, and it's not so obvious exactly how to do this because this is fairly narrow problem solving.
Yeah. So before you move to the next slide, if I could just give a simple whatever reduction of what we're talking about with this inner loop and outer loop business. Okay. So if you look at the maze solving problem on the right, imagine if the inner loop was just learned the algorithm for doing a breadth first search. Okay. And it just simply said, start at the start and color any adjacent non-wall square yellow. Okay. Then basically with each outer loop, you could extend the breadth first search to see all the squares that you could reach just by going one square adjacent to the yellow squares that you already have. And in that fashion, if the path length is 30, then in 30 steps, you could actually just find a path from the beginning to the end. I'm not saying that that's all that it does, but that would be like a super simple version of the inner loop is learning a rule, like your brick that you were saying, right? And so my rule is very simplistic, and it would actually take a fairly long time for the outer loop to do the breadth first search one pixel at a time. But you can imagine that maybe you can then do 2 pixels at a time and say, you know, if I see, instead of just my adjacent pixel, if I see an open path 2 pixels away, then I'm just going to color everything yellow in between me, right? Maybe there's some other shortcuts you can do. And I believe it actually learned not just to find connectivity, but it then like deleted all of the extraneous yellow not on the shortest path from the beginning to end. So it's a little bit more complicated, but I just wanted to give that as like a very concrete example of what might be learned in the inner loop versus what's happening in the outer loop.
Yeah, thank you, Ted. So I'll talk a little bit more about like we have those visualizations on this side, but how do we actually pass that to the model? So the input comes in the form of we give it each problem has its own task embedding. So we have 16 tokens that basically say, okay, we're trying to solve maze now. We're trying to solve Sudoku. We're trying to solve problem 17 from ArcAGI. And so the way that this works, we have one that's for mazes because mazes, you're applying the same algorithm every time. One for Sudoku because you're applying the same algorithm for Sudoku every time. But then we have one for each puzzle of Arc. So Arc actually has 1,000 problems or so. And so each of them is trying to apply a different set of rules. So if we look at this one, like what it's doing is you're saying, okay, find the connection points of all of these grids, but you might have another problem that's saying like, okay, flip it and change the color or something like that. So they're totally unique problems. So it needs a different task embedding saying like, we're trying to solve this kind of problem now. So the first part of the input is the task embedding. So it's a little vector that's saying, do this operation. Then the other part of the input is a 30 by 30 input grid. So this is like some of the problems are actually smaller than this, but they just always padded it to be 30 by 30 because they said that's the biggest out of any of these problems. And so then we have a different embedding for all of the different colors or numbers. So for Sudoku, you have 0 through 9. For the colors of ArcAGI, we have 10 different colors there as well. So each color is then turned into an embedding of 512. So the 512 from there matches up with the 512 of the task embeddings. And then we also have an embedding that represents the positioning. So we have one embedding for it's red, one embedding for it's in the top left corner in this specific position. And then we also have embeddings for which task are we trying to do. So the way that this is input, we have 900 cells from the input grid. We have 16 from the task embedding. So if we're thinking in like language model terms, this is 916 tokens long. That's our attention length at this point. And then at the output of the model, what we're doing is we're outputting the answer latent. So that's still the embedding of the answer. we're doing the embedding of the reasoning. So we have that Z and that L. So the Y and the Z, they changed the terminology between HRM and TRM. So they use them slightly differently. But we output the latent, which is like the embedding of like what's our current state for the answer, what's our current state for the reasoning, and then we also output the actual input that the model thinks. So the model thinks the output grid should look like this specific outcome right now, and then we have another output for whether it should halt or whether it should continue. So it's basically classifying, have I solved the puzzle yet? And so if it thinks it solved the puzzle, then it just stops. It doesn't keep recursing. So one of the things that I want to point out, because I've been putting a lot of focus on the ArcAGI stuff, I've been trying to apply this for that. And one of the strange things with this is the way that ArcAGI is set up is you're supposed to be given example input, example output, and then you get a test input and you say, apply this same reasoning to the test output. But the way that this is configured, where we're saying we're only giving it a 30 by 30 input grid, we're not giving it any examples. So it's a little bit unnatural to say like, we're not giving it examples anymore. We're just giving it the input. And so the only part that is encoding what we're trying to do is actually the task embedding. So we're trying to get transfer on this task just based on task embedding saying like, okay, the core algorithm now is flip and change the color. The core algorithm is like connect the pieces in a certain way. So it's not actually thinking in the way that we think, where we go, okay, look at the input, look at the output. Okay, what's the pattern here? And then we go apply that to the test input. So just one thing that I wanted to point out, because the big limitation here is that you actually can't solve new puzzles at all, because it's limited to, I've learned this specific task embedding to solve the puzzle in this way. So you go to puzzle 1001 and it doesn't have a task embedding for that. And so it can't solve this at all. So that's one of those other key points where it's like you pass this to Grok or to GPT-5 or Anthropic, Claude, whatever. It's going to give a decent stab of with this, it just will have no idea what to do. So it's very narrow. It's not a general intelligence thing. So people are excited about this, but one of the claims is like, we beat these massive models and we only use 7 million parameters. But one of the things that people were talking about on Twitter, and that I realized too, is that the actual like 2-layer block, if you focus in on that, it's only 7 million parameters. But then when we're doing ArcAGI and we say we have 1,000 different problems, and then each of those needs 16 task embeddings, and then each of those task embeddings is 512, you end up with this huge embedding layer. So you end up with 16 million that's just for the embedding layer, and then 7 million for that 2-layer block that's getting repeated over and over again. So it's a little bit misleading to say the model 7 million parameters when actually like the embedding size is huge. So one of the key things that they did in the TRM paper is that they did a bunch of ablations, just cutting apart all of the different things and saying what is actually like giving us this performance benefit. And so the strongest driver out of this whole thing was in HRM. What they were doing was they're saying do this looping pretty similarly, but then only do gradients on the H layer and the L layer once. So just a single like update the H and the L one time. What they figured out is we should actually do the full deep recursion. So if you're saying do 6 loops on the L and 3 loops on the H, do that entire block of 18 instead of just the last 2. And they showed that that gives like way better generalization, way better convergence. And so the idea from HRM was like, if you just update H and L, eventually they'll converge to some fixed point thing. But what they realized is like, actually what you want to do is you want that like 6L, 3H, you want to optimize the whole thing so that deep recursion process does like one step of trying to solve it. So if you do that whole piece supervised, that's like the biggest advancement in terms of better convergence, better generalization. Yeah.
So just a quick comment. So uh, it's really nice to have this smaller model, and especially at inference time. But when we're training the model, when you're training an LLM, actually it's the activations and your optimizer state that uses up the most of your GPU memory. So the fact is, when you get rid of this one-step gradient, and you're basically, if you guys remember RNNs, you're now doing back propagation through time. It means that you have to store the activations for every iteration. And if you're using Atom, then Atom is storing, the whatever the mean and the variance for every one of those. So you can say, hey, this is great. My model only has 5 million parameters. But if you loop it 200 times, it's actually needing to store all 200 of those activations in order for you to be able to then at some point do an optimizer step. And so inference time, it's still pretty small, but training time, it can actually use close to the same amount of memory as if instead of having 2 layers that you repeat 100 times, it's almost the same amount of GPU memory as if you have a 200 layer model with separate, individual weights. Now, there still may be benefit to this architecture in terms of how fast it learns and whatever. But again, just trying to be like clear-eyed about what it is, what it isn't.
Yeah. So they cut out various different pieces of this, but that's the biggest driver. But you can also see, like, one of the things we were talking about earlier, if you change that 2-layer block for a 4-layer block and you do less of the L cycle, you get significantly worse performance. So you drop 10% or something like that. So there's a bunch of little gains that you can optimize with this architecture, but the biggest thing is basically saying we need to train on the full deep recursion cycle, and then we can optimize all these other little pieces. Yeah, go ahead. Yeah.
So I'm not completely understanding this table. The initial method that was the TRM, correct?
Yeah.
And then they tried different variations on that, and they tried different variations on the TRM, and the corresponding reduction in accuracy tells us how much the thing that we cut out, the impact that the thing that we cut out has on how much that's actually carrying, correct?
Yeah, exactly. Yeah, so this was the original method HRM. It got 55%. The final TRM that they came to, so they went through and they said, fix this, fix that. This is the best performance that they got. And then all of these are saying, well, like, let's turn one thing off. Let's change it one piece at a time and then see how important all of the pieces are. So yeah, it's like this one is saying make it 4 layers but 3 loops. This one's saying do the adaptive compute. This one's saying, in the original paper they had the same like 2-block thing, but they said do a different one for H and a different one for L, and they figured out we can just say it's the same layer for H and L. So that's the whole idea of this table, is basically saying cut a piece out and see how much it hurts it, basically.
Okay, thank you.
Yeah. So Ted's point about depth and the memory. So you want to train on this full deep recursion, all of the H's, all the L's in a single of those outer loops. That seems to help with performance a lot, but the difficulty is you end up spending more and more memory as you go deeper and deeper. So if you want to do 3 H loops and 6 L loops, you end up doing 18 depth of the 2-layer, and then you might do multiple on top of that of the 16. And so you can end up with this 84 depth where you're going very deep and you have to capture the gradients at all of the different outer loop parts, and eventually you just run out of memory. So you want to have supervision through this massive depth at various different points, but eventually you just run out of memory. You can't do it anymore. So it is like it's 2 layers, but repeated so many times. And then if you say I want to get supervision at all of these different points, eventually you run out of memory. So it's very helpful and it scales well, but eventually you do run out of memory still. It's not like 2 layers, so it's just 0 memory. It's you still have to capture that depth basically with the memory somewhere. So comparing to the other state-of-the-art models, this is the part that really got a lot of people excited. Was you say, okay, DeepSeek R1, that was so powerful. It was this reasoning model that came out of nowhere. It gets 0 on Sudoku, 0 on maze. It just can't solve them. It's too many steps. It has to get all of the implementation correct. And then the other thing that they're comparing to is saying basically take our existing model, but instead of doing like all of the looping, recurrent steps stuff, just say make it 12 layers or whatever, and just try and solve the problem in a single pass and train it to do that. And same thing, it gets 0% accuracy, 0% accuracy on Sudoku and maze. And so HRM got a boost, and then TRM, they did one version that had attention and one version that had just an MOP, and they said, okay, look, we can do even better on Sudoku. On maze, the MOP doesn't work for some reason. But then the ARC stuff, similar thing, where these models actually get some amount of accuracy. They're able to kind of figure out what these puzzles are about, but you can strongly beat them with the right TRM setup. So the TRM with attention on ARC2 can get 7.8%. And so that was one of the pieces that people were like really excited about, was this ARC AGI2 problem is so hard. Like most of these models just totally fail at it. But with this tiny model, you're able to train it to actually do these things. So one piece that I wanted to touch on in regards to the LLM stuff. So if you look at DeepSeek and Claude and O3, all of these are autoregressive models. So what they're doing is they're outputting one token at a time. So they might internally say, do some thinking and then output the final grid. But ultimately what they're doing is they're just saying left to right, output one more grid, one more grid, one more grid. So one of the problems they have is they don't have a 2D view of the board, and they're just trying to solve it like sliding across. And so that's kind of difficult to do. So that's one of the advantages of TRM, is it's actually able to look at the whole board and understand the 2D relationship, versus GPT-5 is just saying one token at a time, and it needs to just scan across from top to bottom. And so that can make it difficult, because sometimes it's actually easier to solve the problem like wholesale than it is like pixel by pixel. It needs to get every single one of the pixels correct based on the previous ones. So that makes it more difficult for those models. So there's a ton of stuff that's been happening on Twitter and other places. So I won't go into super depth on them, but I'll just kind of touch on some of the topics. So the HRM was such a big deal that the people from ARC directly said, like, let's try to run this and figure out what's actually going on. So they made this whole article that's basically digging at all of the pieces, saying what drove this performance. Similar to TRM, they just said, okay, there's lots of stuff. You're saying it's inspired by the brain. What's going on here? So they studied a bunch of stuff, and the actual people who put on the ARC AGI competition said, let's run it and see if we can reproduce it and what the core pieces are. So this is a cool animation someone made just recently, showing it going through the loops, trying to solve the problem. So you can see it's going through and trying to solve loop, 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 and then eventually trying to get to the answer. So people have taken the HRM model and they've already started figuring out, how do we apply this to other things? So it's only been trained on those 3 things, but they said, okay, can we do reinforcement learning on top of it? Can we train it to be a language model? So people have already started exploring, like, how do we make this into something that's more useful than just a puzzle solver? So here's some of the people on Twitter have been just taking the model and saying, like, okay, can I make a tweak and then train it and reproduce it? And then other people have been saying, take the existing checkpoint of the model. How can we extend this? So the way that it was trained was only 16 loops, but they figured out it's still stable and can continue trying to solve the problem for even more steps. So they figured out at 16 steps, it gets 84% accuracy. But if you extend it to 64, 112, 224, 448, it gets all the way up to 97. So people thought that was like extremely powerful, that it's like we only trained it for 16 steps, but it's so stable that we can just say keep looping and it will just keep trying to find the solution. So it's this interesting kind of search pattern where you can just say, okay, just keep going until you think you actually have the answer. And it was able to get even better performance. Yeah. It's 16. So the question was, what do I mean by the 16 steps? So it's 16 deep recursion steps. So it's doing the L cycles, the H cycles, and then on top of that, it's training potentially for 16 loops of that per sample. So it's only ever been shown like trying to pass its input into itself 16 times, but they showed that you can actually recurse even more and say, do this 400 times or 900 times or something, and then it can just keep trying to solve the problem. So that's a very big deal that it's able to just extend into even more and more effort on certain things. So one of the cool things with this, they actually, this came from a researcher from Samsung, the Samsung AI lab, and they measured the impact of this paper. So they showed that this actually had a big impact on Samsung stock. So you can't attribute it all to this specific paper, but it's pretty amazing that they went up 15% after the release of this paper. So this just came out today. Someone made a website that is showing some of the solve attempts of the TRM model. So if we look at this, we can see what was the input, what was the output, and then they also show like, here's all of the steps of it trying to solve the problem and whether it thought that it had solved the problem or not at that point. So yeah, that's it for TRM. Any questions on that? Anything else we want to go into? Yeah.
Thank you for presentation. Could you please scroll to architectural diagram of that model?
This one?
Yeah.
Yeah.
Do you have some kind of intuition how it's possible to sum up like input prediction and latent, and also like if you go to the code, like slide up, I think in the first function you have like net function, and I think it's same function, right? And in first case it uses X, Y, and Z, and in second case it some kind of change like Y to Z. So like how it's possible? Do you have some kind of intuition behind that?
So the general idea seems to be that they're learning their embeddings separately so they can orient themselves however they want within that 512 size. But it is during this step, it's just adding up X, Y, and Z. And in this step, it's just adding Y and Z. And that is the way that the network knows to change its behavior. So at this step, it's updating its reasoning, and it knows this is the time to update its reasoning because it has the X passed in. And at this step, it's not given X, and that's what triggers it to try and output the updated prediction. I've looked at this a whole bunch. I don't know exactly why it works like that, but that seems to be the setup that's working. Yeah.
Hey, Ryan, quick comment. This actually technically isn't the entire code. This is the entire thinking code. What they're not showing is that the board is actually goes through an embedding layer. Okay. So this is not the raw board. This is the board in some embedding latent space. And so hypothetically, your X's, Y's, and Z's could all be in like orthogonal subsets of that 512 space. Like intuitively, you could say the board maybe only takes up the first 256 and the Z takes the last, 64, whatever, right? It doesn't have to be aligned that way, but if they're an orthogonal subspace, then you can just do plus and they don't interfere with each other at all. Does that help?
Ryan, since it's a reasoning model, other than these use case of maze, Sudoku, etc., where has it done good work? Like as you said, it is not that good in chatting, like not like GPT. Where else we can?
So the idea, this paper only came out, I don't know, a couple weeks ago. So people are still figuring out what is this actually useful for. So people have started with can we even reproduce this? Which are the successful parts? And then the original author is saying, okay, let's figure out how to extend this to actual text LLM stuff. So I don't think that it's that big of a jump to make it a text general model. It's just passing in different data basically. But the difficulty is you still need like what's the solve state, and then on top of that, you're not getting general knowledge packed into these two layers. So eventually they'll have to extend it to 6 layers or 12 layers or whatever, and maybe they can keep this looping process, but it's unclear if it's going to be useful for like language reasoning.
Yeah. Yeah. I mean, right now they're focusing a lot on Arc because Arc is one of the harder problems that you can't use, GPT-5 for. But I will also caution that this is like a BERT model in the sense that it's using encoders and it has a fixed context length. So there is something you need to fundamentally change if you're switching it to be a generative model that's not just with a fixed input size. And so I have some reservations, some concern that a good chunk of the gains they got was just by reformulating the problem as a fixed width problem instead of, like Ryan mentioned earlier, spitting out one token at a time. So it's a good thing to do if you're trying to solve ARC, but it then means that if a lot of the gains were from just problem formulation, it has nothing to do with your actual neural network. So we'll see. But we wanted to cover this because it's a pretty hot topic, and I think it's always very interesting when you don't just see like, oh, look, Quen 3 has this one little tweak and we changed, I mean, don't get me wrong, they're all good tweaks. It's like, hey, we reduced the amount of memory by 5% by tweaking the way we alternate attention layers. And we reduced this, by 5% by tweaking that. But they're not really doing something. Here is something just so radically different so that it's worth paying attention to, and time will tell whether this really pans out or not. But yeah, we wanted to cover it because it is so different, and that makes it more interesting than just when somebody has a very slight tweak to otherwise the very standard, attention step.
Okay, cool. So I have no other questions on that. I do have ML news this month. I realize I need to update the date on that, but I'll run through this super fast because we're already over time, but I think this is one of the more fun parts of the meetup, so I'll still touch on some of these things. So we've made it a habit of just every month I'll do ML news, all the cool stuff that's come out in the past week. So one of the things that's recently come out, OpenAI Atlas. So this is OpenAI's browser. So they're basically saying we need our agents inside of browsers. Let's let GPT-5 or some other model take control of your browser and do tasks for you. So you say, go book this flight or whatever, and it will go click around the page and do all of that stuff. Yeah, you can download that. They released their GPT OSS safeguard. So a while ago, they released their open source model, and they said, everyone train this, do whatever you want with it. Now they released the safeguard model, which is supposed to be like it's just focused on safety. So it's all of the rejection stuff for like, oh, you're asking me a question I can't answer and stuff like that. So it's supposed to function as a filter for whatever you're trying to reject the model from doing. So one of the common topics that we'll see across all the different companies is they all started various security efforts. So OpenAI's is called Aardvark. It's this idea of like, let's make an agentic coder that's just focused on code security. So making sure that you don't have some bug that allows private information to be leaked and stuff like that. So Aardvark is this idea of like, let's go audit everyone's repos and then make sure that they're safe and secure and not leaking passwords or private info or whatever. So I'll skip to the other pieces just to show like every company is doing this right now for some reason. Where'd it go? So Anthropic has the same thing, building AI for cyber defenders, similar idea, go audit people's code and make sure it's safe. And then Google also has their own, they're calling CodeMender, AI agent for code security. It's interesting that they've all released this in the same month. So I don't know if some event happened that triggered them all to focus on this, but it's interesting that all three companies have popped up at the same time saying, let's focus on code security. So OpenAI has been going crazy with all of their data center expansion. So they're opening one up in Michigan. It's supposed to be like more than 1 gigawatt. So huge amount of GPUs, huge amount of power. They put out a blog post for this OWL layer they're calling. And so I don't exactly understand how this works, but it's some interaction with Google Chrome in order to make it faster and easier for them to interact with the browser. So they've got some crazy engineering going on so that they can run the Atlas browser and that stuff, it seems like. One of the big pieces of news, so OpenAI has had this weird history of like nonprofit and then back to for-profit, and now they've configured things so that the nonprofit owns the for-profit branch, and they're people are excited about it or have mixed feelings about it because this is now the best funded nonprofit that's ever existed, basically, because they as their inception have been given a certain amount of OpenAI stock that's worth so much. So now they're like this massive, potentially philanthropic organization. So OpenAI trying to break away a little bit from NVIDIA and AMD and all of these other people. So they partnered up with Broadcom and they said, basically, we're going to try and make our own AI chips. But at the same time, they're also teaming up with AMD and saying, we'll deploy a certain amount of AMD chips and we'll start training on those and we'll just consume a whole bunch of capacity. So they made this partnership, and a lot of people were talking about the interesting element of this is that if the correct conditions happen, then OpenAI will actually get a very significant amount of AMD stock. So OpenAI saying basically, we're going to make these massive data centers with your GPUs. If AMD's stock goes up a certain amount and OpenAI commits to a certain amount of capacity, then they get this huge amount of AMD stock. So it's a very interesting arrangement where OpenAI could get a huge chunk of AMD. They also released AgentKit. So this is their like agent builder. So they built this like little workflow diagram builder thing where you could say, basically, I want an agent to do this certain sequence of tasks. I want it to read email and then pass to this LLM and then do whatever. So AgentKit lets you build out the whole workflow and say, like, do these certain sequence of steps, and you have if, else, and all the different stuff that you might want to do with that. So people have started playing with that and seeing what they can make possible with this sort of workflow builder. Another one that people are excited about is this ChatGPT apps. And so this is basically the way a lot of things have worked is they have this website and then it's got some ChatGPT integration. This is kind of inverting that, saying basically ChatGPT is now a wrapper around everything else. So if you want Zillow, you say basically, okay, do this thing, and then Zillow uploads like whatever I need. Like I need to do a search of houses in this area, and then pull that back in and get some result back. So they're kind of embedding other websites instead of ChatGPT. So moving on from OpenAI, Anthropic released Claude Haiku. Looks very powerful. It's basically a shrunk down version of their best models. And so what some people are excited about is it's pretty cheap, and it's supposed to be as good as their last Sonnet model. So that's a very big leap if you're able to make it so much smaller, so much cheaper, and then say this is as good as the best we could do 6 months ago. So OpenAI had all of their partnerships with all of the other companies. Anthropic is partnering up with Google Cloud and committing to buy a whole bunch of TPUs. So this is a big departure because Anthropic has been very heavily linked with AWS in the past. And so this is them kind of jumping ship a little bit and spending more capacity on Google Cloud. And this is a big deal for Google Cloud because historically they haven't sold their TPUs. You can rent them, but they didn't do this sort of like buy a bulk, like thousands of these deal. Anthropic also released agent skills. So this is the idea of you have these little composable pieces that you can basically just give to Claude and then say, do this little thing. So if you want it to behave in a certain way, you say, here's my skill to like follow my brand guidelines in a certain way, or here's a piece of code, just reuse this whenever you want to do certain things. So you can upload your skills and then it will try to use the tools you give it rather than just the ones that it's been pre-configured with. Meta didn't release that much because they just had a massive layoff. But one of the cool parts that they released that people have been excited about, they have all of these pieces, but the part that people have been excited about is this one called Monarch. And so the idea here is basically we have these massive like server setups, but it's very difficult to interact with them. And so Monarch is supposed to be this sort of orchestration layer. They're excited because it's like we can just go from our laptop and then control 1,000 GPUs and it works out of the box, because a lot of the pain with these model training runs has been how do we actually like orchestrate 1,000 GPUs all at once. So that's supposed to be a big piece for people.
Can I make a half snarky comment? So I think the old FAIR people that did not move over to the superintelligence team that got laid off, the new team seems to actually be producing a lot of papers, but I feel like it's very spammy. I feel like the quality of the recent superintelligence papers has just been like this giant paper dump and not up to the previous threshold for releasing papers.
Yeah. I saw a bunch of activity on Twitter of all of the people that were laid off, and it was interesting. One of the papers we talked about last month was actually the lead author was one of the people who was laid off. So the deep comp thing that I talked about last month, the lead author of that got laid off as part of this. So interesting how it's all connected. So Google update to VO. So we've talked about this model in the past as a video generation model. They're just iterating and saying new version, a little bit better. And then one of the other things that we talked about previously was Genie 3. Genie 3, this model that it's a video generation thing, but it's very interactive. You can actually go and just control the environment. So you can say like arrow key forward, look left, all of that stuff. So you're in this like live generated world that you can just walk around like it's a video game. It just got named one of Time's best inventions of 2025. So pretty interesting that that has happened so quick because it wasn't released that long ago. Bunch of Twitter links. So this one is talking about how they think that GPT-5 is the first major model that has actually been trained on less compute than the previous one. So GPT 4.5, huge compute budget. They threw a bunch of money at this, and then GPT-5, they say actually is the first time that they haven't just been increasing at this exponential slope. So GPT-5 actually used less than the previous ones. At least they're estimating. One of the big things that's been going around the past few days is that they figured out that the reinforcement learning that a lot of people have been doing, it's reliant on doing predictions of the model and seeing how the model does and then correcting based on that. And so they figured out that everyone's been using this BF16 format of their numbers, and they realized there's actually a big departure between the BF16 and the FP16 results. And so they were showing like you just get complete divergence actually. And so if you just switch to FP16, then you end up getting much smoother, more convergent results because what you're doing inference with and what you're actually like your model representation is slightly different. And so the past few days, everyone's been freaking out saying like all of our RL results are invalidated. So people have been figuring out what's going on with that. One of the things that I'm most excited about is from Cognition. So this is the company that put out Devin, which is like the high-end coding assistant that's supposed to do a bunch of stuff for you. They output this model that is supposed to do code search for you very, very fast. So there's kind of two different ways that people have been doing this. One of them has been RAG, which is basically like take your code, embed it in some way, and then do similarity search and hope that you find the right code that's relevant to whatever you're doing. And then the other end of that approach is like, my model's so smart, just have it read all my files and try to find what the correct piece is. But that agentic search, what they call it, is very slow because you have to go through and the LLM has to go process your entire code base. And so what they figured out they can do is they can train a model specifically to do just the code search, and they can make it much smaller, and then they can also do it in parallel. So if you want to, you're not limited to a single model. You can say, I have this tiny model, apply it to 16 files at once, and then it's all reading different pieces of the code. And so in theory, you're getting the quality of the agentic search, but you're getting the speed of the RAG, or at least closer to it. So people are pretty excited about this because it can find the relevant pieces of code that it needs to change when it's trying to do things very quickly. So we've seen, this was mid-October, we've already seen other companies trying to scramble and get similar models out. So this is a very exciting one. I've talked about some of the robotics stuff in the past weeks. This one's just crazy. So we've talked about Unitree and other companies that are selling robots, but they come out of the box doing functionally nothing. You have to program them to do whatever you want. This one is trying to take sort of the Tesla approach, and the idea is that it's going to be teleoperated by a human. So you have this robot in your house that is being operated by someone in the Philippines or wherever, and they're looking into your house with the cameras from this robot, and then they're actually acting out whatever task that you want. So very, very strange setup. But the interesting thing about this that people are very excited about is a lot of these robots in the past, it's kind of like, oh, this is a cool tech demo, but you can't buy this. This you can actually buy right now, $500 a month or $20,000 to own. And it doesn't ship for another year or so. But this is something that you can actually buy, and it will hopefully show up to your house. And people are having all their reactions on Twitter to like, do you trust to have some other random person kind of teleported into your home? And the idea being that person's going to do whatever task you tell them to, and then that's training data to go train the model to do those things autonomously. So that's the idea there, but I think it'll be interesting to see if people are actually willing to have like a robot remotely operated in their house at all times. So another big drop just from a few days ago, this company Xtropic, they have a founder that's been very public on Twitter and just saying everything's broken. And so they finally released actual hardware. And the idea behind this is with like quantum computing, they have qubits, but they're saying, okay, we can actually do a similar thing just with thermodynamics. And so they have these things that they're calling p-bits. And they're saying we can make sort of a like pseudo quantum computer that runs at room temperature, and it's going to be so much better for all of these like machine learning tasks. It's 10,000 times more efficient and all of this stuff. But the difficulty is right now they have these very simple, very low capacity devices, and they're trying to work up towards bigger and bigger devices. But it's difficult because you also need completely different algorithms. It's no longer you're just like GPU matrix multiply stuff. So very interesting work. They released a paper and everything, but it'll be interesting to see if anyone's actually able to make anything of it, because it requires a lot of steps to fall into place. Two different papers. So this is the TRM one that we just talked a whole bunch about, and then someone in the Slack linked this one ruler paper. So there's this ruler benchmark, and the idea behind ruler is basically you want to be able to see if it can handle very long context. So if you give it an entire book, is it able to answer a question from that book? All of the tests, like the ruler test right now, is focused on just English, but this one is focused on multilingual. So is it also able to handle long context in Spanish and French and all these other languages? So interesting work to see if there's actually different performance between English, because English it sees so many examples of, and then these other languages it might not have as good of performance in. So final segment, I'll be quick with this. Lots of top Hugging Face models this week. So Minimax, company that has put out a whole bunch of good models recently. So they were the #1 this week, which is pretty interesting. They released a model that looks very good at coding. So people have started adopting this a little bit. And then I would say that this month was definitely the month of OCR. So DeepSeek released an OCR model that people are excited about. Paddle OCR, another one that came out. This other one, Chandra, also OCR model. And then this Light-on OCR model also came out. And then the one that I'll touch on that's kind of interesting is Glyph. And it's similar in that it's trying to look at text from an image, but then it compresses it to your more LLM focused view. And what they realized is we can get the same performance out of image tokens as we can text tokens, but even more compressed, which people have been trying to figure out because it doesn't really make sense. So the idea here is I have some text, I render it to an image, and then I have the model read it, and it's able to understand that better than if I just gave it the text directly. It's more compact representation. So something strange is going on there because they're saying, look, we can get the same performance from 240K text tokens out of 80K image tokens. So some weird compression is happening there, and people have been trying to figure out what's going on there. More video generation models. Those have been big. GLM, so they released another big model. Lots of just iterations on what's been coming out, trying to keep state of the art, pushing 1%, 2% on everything. So people have been playing with different forms of attention. So some of the interesting moves has been actually moves back to dense attention. But this one is focused on linear attention. So different trade-offs in terms of sequence length. This LADA 2.0. So this is a diffusion model. So we've talked about like the autoregressive language models. They go left to right. These diffusion models, they just kind of pop in multiple steps over time. And so these are very interesting in terms of they can generate very quickly because they're not limited to one token at a time. AMD released a model that ended up in the top 20. So that's interesting because they haven't really been known for releasing models in the past. And then we talked about this one already, but this the GPT OSS safeguard, talked about it earlier, but this is showing up. People are actually using this, so that's interesting. So that's it for the news. Thanks, everyone.
Awesome. Thanks, Ryan. Thanks, everyone, for staying late. Did anybody have any questions for Ryan about the monthly ML news?
Can you explain more about the whichever of those models was the one that had the weird compression?
Yeah, so this is they found this in actually both of these models. So the DeepSeek one and Glyph. I don't know exactly the mechanism that this is possible, but your typical text, it's taking the text and then it's splitting it into tokens and then it goes through your LLM. It embeds it and then it does all the transformer stuff. With Glyph and with DeepSeek OCR, what they figured out was if you actually take your text and just render it to a JPEG, and then you pass that through the vision processing of one of these OCR models, it can be represented in less tokens than if you just actually had the raw tokens and split it into chunks, which is very bizarre. So the way these image models typically work is they'll cut the image that they're looking at into 16 by 16 little chunks of the image. That becomes a token. And so what people are realizing you can do is you take your text, you make it a tiny little, like you downscale it. So you're taking like 8-point font or something like that. And then you can fit 3 words in one token or something like that. And then it's this weird compression where it's able to get a denser representation than if you just directly gave it to them. I don't know exactly how it works, but people are very surprised by this result because you would think you gave it text directly. Why would it be more efficient to read it from the page than to just give it words?
Yeah, and I mean, if you think about it, maybe you have a common word like brain, that's a token, it's just one token. But if you say brains, maybe now you need 2 tokens. But that might, brain might, be reasonably well compressed. But the fact that, you know, saying brains now requires double the amount of tokens, visually, maybe you can compress that and not. I will comment that byte pair encoding comes from the compression world, comes from the communications world in terms of what is sort of the optimal coding for information that you need to send. So the most common things you want to have very short representations, and then the very rare things you can afford to have longer than average. So if you have like 255 things, you know that you can represent them all uniquely as 8-bit things. But if something's super common and you represent it 1 bit, and then some of the other things might need to be 9 or 10 bits, you actually win in the long run. That's true of the BPE algorithm, but we use BPE to define the vocabulary, and then we give every token the exact same length. So you can't say that because BPE is a compression-inspired algorithm that it works well for LLMs, because we actually threw away the part where common things get shorter representations.
I had another question. It was about like the research that was going on. Like we had a thing that where you mentioned that the quality of research or the topics that they were doing on research were not like, relevant to what's going on right now, because I think timing is everything, right? But maybe their thing is not meant for this time. So how do we like stay relevant with, the kind of research that we are putting our efforts into, so that we don't end up like spending time for something that is meant for the future rather than now? So living in the present kind of thing.
I don't necessarily have a good answer for how do you keep up, because there's so much stuff going on. One of the things I remember reading a year or a couple of years ago was they interviewed some really big names, famous professors, Andrew Ng or whatever, and every one of them said that actually they actually can't keep up with everything. So one of the things that everybody does is a little bit of the test of time. So if your area is, let's say, OCR stuff, then maybe you're reading all the OCR papers. But for other stuff, you just can't keep up. And so then it's like, wow, there was this new hot thing. Well, I'll wait. If a month or 2 from now people still say that was really great, then I'll go and read it. But I can't just read everything, as it comes out. I don't know if you have any other advice.
Yeah, I think is one of those things where it's like if it's something you remember, then it must have been important. And like a lot of the papers, there's just such a big fire hose that I'm sure that there's like key findings that people are totally missing. Like someone puts out a paper and just no one ever reads it. But the stuff that keeps coming up over and over again, like this TRM stuff, I saw it once on Twitter, and then it's just like this is what everyone's talking about for the past however long since it came out. So it must be important because just the community has said, okay, this is interesting in some way. It's pretty difficult to just like pick the paper yourself and say there's 1,000, this is the good one, you without like reading every single one. It's just impossible.
Yeah, another example would be, oh, somebody comes out with a new variation on attention. If you just wait a year, and if, you know, Quen and Claude and every single model is using that new variant, well, then it probably worked. And if everybody's talking about it, but a year from now, still nobody's using it, then it probably didn't, in the grand scheme of things, make that much difference. I don't know. I do have some things that I've seen where I'm like, I'll throw out truncated rope embeddings. I think they work better, yet people aren't using them, and so I don't know why. Maybe it help. Maybe it doesn't help. Maybe it helps 0.02%, and so people are just lazy and they're like, I'm not going to change my code for that tiny bump. All right. Thanks, Ryan.
All right. Thank you, everyone.